Okay, our next speaker is going to be John Loftin from Rutgers University, who will speak on some projective invariants of convex domains coming from differential geometry.
Thanks, Dean. I'd like to thank the organizers for the invitation, and I guess I will be, this one I think is being filmed, so I think my inability to control the boards will be preserved for a long time. So, and again, I mean, similar to Anna's talk before, I mean, this is going to at least start out mainly as kind of a survey talk. I'll take some time to make definitions because I don't think most people here know the details yet. So I will. So projective invariants of convex domains, and I guess one thing that I may start with, I mean, I'm just going to just to mention is something that people here should be very well acquainted with, which is, I guess, the Hilbert metric. So the setting, this should be convex. So we're going to have omega is going to be so you choose kind of an inhomogeneous chart on Rn and RPn, and you choose omega, so this means kind of properly embedded. So this is going to be a convex domain. So then the Hilbert metric, even you can describe this as a Fensler metric, which is singular in general, but or also kind of as a metric space metric. It has very nice properties. It's complete, it's geodesics or straight lines, and it's very nice. But what I'd like to talk to you about is a different metric coming from affine differential geometry. And so this you might call, in various places, it can be called maybe an affine metric, or sometimes a Blaschke metric, because I mean Blaschke, I guess maybe around 90 years ago, I mean he was one of the main early proponents of affine differential geometry. So let me describe this. So this will be a Riemannian metric, a C infinity Riemannian metric on such a convex domain. Okay? So I'm going to give, at least first to start out, I'll give the a quick definition of this, and then, I mean, depending on how much time I think there will be, or if there are questions, I can give a different definition later once we have a little bit more machinery. So, so what I want to do is I want to solve this in terms of a differential equation. So omega is a bounded domain, and what I want to do is to solve a certain Dirichlet problem for a Monge-Ampere equation. And so this is going to be so I'm going to solve for a real-valued function u, which will be convex, and the equation is, so uij is just the Hessian. So the Monge-Ampere operator, the real Monge-Ampere operator, the determinant of the Hessian is this minus 1 over u to the n plus 2 power on omega, and then so then we have kind of this Dirichlet condition. So u is equal to 0 on the boundary, and of course u is continuous to the boundary, and also of course we want this, or at least for this sort of analysis that I'm going to be talking about, we really need this equation to be elliptic, or else you can't really start. So the condition is that U is convex. Okay? All right. So this can be done So Cheng and Yau, I guess, in the late 1970s, solved this Monge-Ampere equation. And this was, I guess, one of the first general solutions to real Monge-Ampere equations in the paper where they solved this equation. And I guess there's also some earlier work of Loftin and Nierenberg, in kind of a special case in dimension 2 where the boundary is nice. But you notice here on this omega, I do not assume any boundary regularity beyond what you get from convexity. So the boundary is only Lipschitz. Okay, so now, let me see if I can get this one. Whoops, that's the wrong one. Okay, so now what do you do with this, this equation in order to get the metric? So I guess the existence, this can always be solved. Actually, I guess the next property I should talk about, that uniqueness for solutions to this, for this Dirichlet problem is, this is an easy application of the maximum principle. So you just consider two solutions. If they, you consider the max. If there are two solutions, you consider, say, the maximum point of their difference, and you show that that has to be non-positive, and then that's enough to do this. So, all right. Then I guess the affine metric is given by the following quantity. So minus 1 over u times the Hessian, and I'll use kind of t coordinates on omega. And so this is, so when Cheng and Yau did their work, they knew that this equation, they wanted to study this equation because they understood the affine differential geometry. I'm not sure if Loftin and Nierenberg did this, but they knew already that this metric, if you solve this equation, this metric is projectively invariant. So it is possible, if you are analytically minded, to come up with, well, it has been done that people have come up with the fact that this is a projectively invariant metric without referencing the geometry. And so it's going to determine a convex hypersurface in Rn plus 1, which is going to be asymptotic to the boundary of the cone C over omega. Yep. U is negative. U is 0 on the boundary, but it's a convex function, so U itself has to be negative. Yeah. So yeah. So I think so. This is at least positive. I mean, I don't think there are other errors, but that's possible. At least that's not one of them, I think. So, sure. Any other questions? Okay. So this is a convex hypersurface asymptotic to the boundary of the cone over omega. And the picture that you might think of here, well, the coordinates in omega, if you have an inhomogeneous chart, you naturally think about this as kind of an affine slice. So this would be the origin in Rn plus 1, and omega is just going to be in an affine slice. And the convex hypersurface is given by the radial graph of this quantity minus 1 over u. And so in other words, it's going to be given by, so I'll call this H. So this is going to be so you just kind of multiply by this factor these points in omega, thinking of this as sitting in an affine subspace in Rn plus 1 in the standard way. Okay? And so this is called a hyperbolic affine sphere. All right. So I guess a few things to talk about here. I guess the fact that this is asymptotic to the boundary here, and this H will look something like this. So U is negative, so so minus 1 over U is positive. U goes to 0 at the boundary, so minus 1 over U goes to plus infinity at the boundary. And that's where you get the asymptotic to the boundary of the cone. I guess another thing is if you have, there are kind of some standard homogeneous examples. Which are both quite important. So the first one is if kind of omega is a ball, then C is a round cone, and H is just the standard one sheet of a hyperboloid, right? And so this, I mean, this is one example of this. Another example is, and so this is quite standard. Another example is due to, I guess, Titseika more than 100 years ago in dimension 2, but kind of Calabi and other in higher dimensions, is that if you're kind of if you're in kind of the first orthant of Rn plus 1. So C is going to be the first orthant. So in other words, that's going to be the first orthant is just where all the coordinates are positive. So of course, this is a convex cone, and if you think about it, it's a convex cone over a simplex. You just have to tilt things a little bit. So this is going to be, so omega is going to be a simplex in this case, and the H is going to be the product of the xi's is going to be some constant. And I'm not kind of, there is some, this constant is not as nice as you would like it to be, but it's easily described. So you can think about this, if you think about this, I mean, just this would be, I guess, the first octant in R3. And you may kind of think about this as, so this hypersurface is asymptotic to each of the faces of this octant and also to these. So you can think about it, it's kind of like a, and I may not be able to draw this. Oops. But it's kind of like a cobweb hanging. It's kind of it comes very close to the this corner of the room, but it kind of goes up asymptotic to each of these faces. Okay. All right. So I guess there are, maybe I should talk about some properties of these examples. I'll do this in a color. So for this first example, where kind of this hyperboloid model, this has, as you might guess, this metric has constant negative curvature. And kind of the, naturally, then this is kind of one of the descriptions of model of hyperbolic space, and hyperbolic isometries act on it. So there's not really any other choice but for this to be a hyperbolic metric. And in this Calabi-Titseika example, this one will be, this metric, it will be flat. So these are, and so if you think about this, these are really the extremal cases of convex domains. Either you have a ball, which is as round as it can get, or you have a simplex, which is kind of as angular as it can get at some point. And you have kind of these curvature properties. So I guess maybe the next thing I should talk about some more. Whoops, that's the wrong one. So in general, there are some nice curvature properties here for these hyperbolic affine spheres. Or the metric induced. Okay. Okay. So I guess one thing is, so let me just list some more properties. The metric is complete. Is this visible enough? Okay. And so this is due to Cheng-Yau. And I guess there is also a curvature property. There's kind of a uniform constant that only depends on the dimension, such that the Ricci curvature is bounded between this negative constant and 0. And so this is due to Calabi. I mean, it seems unlikely that you're going to get a bound on kind of sectional curvatures. That's kind of too much to ask. I mean, as you might hopefully guess by these two examples. But at least the Ricci curvature is uniformly bounded. That's possible. Okay, well, that's possible, yeah. Okay, yeah. Okay. So I guess perhaps live near Nuremberg. Let's see. I guess another thing is that kind of H itself, this hyperbolic affine sphere, this is going to be invariant under, I guess, special linear actions on the cone. And then, of course, H itself is diffeomorphic to omega under projection, and so natural tensors and other quantities that live on H just project down to omega and become projectively invariant. Okay? All right. So there's another kind of invariant, which I'll probably explain a little bit more later, is that there's a so there's an invariant cubic tensor, which is sometimes called pick form. And this is a tensor of the form. Well, I mean, I don't really distinguish between. I mean, there's only one natural metric, Riemannian metric, so I don't distinguish so much between whether the indices are up or down. So I'll just put them all down. And this is a kind of symmetric. This is a symmetric 3 tensor, and this is. And so there's a property of this that this cubic tensor is identically equal to 0 if and only if the hyperbolic affine sphere is a hyperboloid. And let's see, I think this is due to Burwald and Blaschke. This is kind of an old property in affine differential geometry, and it's true more broadly in affine differential geometry than just among affine spheres. So you can define this for any convex hypersurface, and this theorem is still true. Okay. Well, I guess it's true that it's a hyperquadric, not necessarily a hyperboloid. Okay. And then I guess this cubic tensor, it's kind of maximal in norm. And I guess I didn't, this is the case, the Calabi-Tsetsika example. And I'm not sure if it's known kind of the other way, whether kind of maximal and norm implies that you're in this Calabi-Tsetsika example. But that's, I mean, I just thought about this yesterday, so I didn't have time to search the literature on that. The next thing I'd like to talk about is that these hyperbolic affine spheres satisfy a rather strong duality condition. And that is that we have so given this hyperbolic affine sphere H, which is a strictly convex hypersurface, we can define what's known as a conormal map, which is kind of closely related to the Legendre transform. So if X is a point in H, then the conormal map L is going to live in the dual space to capital Rn plus 1, which I just write the subscripts down. And this will satisfy the property that L of X is equal to 1, and L of the tangent space to X is mapped to 0. And so this completely describes a dual vector here. So under this conormal map, if you so this is kind of L at X. This map L, and my notation isn't exactly great here. This L of H in the dual Rn plus 1 is a hyperbolic affine sphere associated to the dual cone, C star. So if you take, so this is kind of, and so of course there's the notion of projective duality for this, these convex domains, and so this duality is, so this is a hyperbolic affine sphere. This map is an isometry with respect to the affine metrics. Okay? And so this duality is, I believe, due to Calabi, but it was, I think in the literature it's in a paper of Jejena. Okay? All right. So let me put this one up. It's very hot. So I guess I've been talking a little bit about kind of these properties of hyperbolic affine spheres. There's also kind of a way of so this there's kind of a local to global principle here, and so so I guess maybe one of the things that I first might do is to define the to say how to get the affine metric. So given F, kind of an immersion of H, which is the hyperbolic affine sphere, then and X and Y are tangent vectors. And D is the standard flat connection on Rn plus 1, then what you can do is you can consider, I mean, and there's a way of kind of extending this so that it doesn't depend on choices. So these are kind of tangent vectors to H. So there's a way of extending this. And so what I want to do is I want to do kind of a similar game to what you do in Riemannian geometry, I want to consider the tangent part and the normal part. It's just that in affine geometry, we can't rely on the Euclidean metric in Rn plus 1. And so what we're going to do is we're going to use a splitting instead. So what we're going to do is we're going to use kind of the span of f in this case, and then we're going to talk about kind of the tangent part. So maybe the tangent part to f at h. Okay? And so when you do this, I mean, you have kind of, this is a connection term, and this is a second fundamental form term. Okay? Okay? And so it's easy to see that this is always a torsion-free connection, and this is the second fundamental form. So since H is strictly convex, then this shows that this is actually a Riemannian metric, and this is the metric that you get that I've described above. So this is the affine metric. So maybe, or sometimes it's called the affine second fundamental form, because I mean the first fundamental form depends on the Euclidean metric, so it's not really used. And this is this connection is also an invariant. And it turns out that this connection is, just from the basic properties of this equation, this connection is projectively flat. And the geodesics of this connection are, when you project them down to omegas, are straight lines. Okay? And then the cubic form is, and I'm probably going to get the sign wrong, is at least, I mean, and I'm also not going to, this is going to be a different variation of indices than before. So if you take this connection, which is projectively flat, and you take the Levi-Civita connection of the affine metric, and you subtract them, then that's an invariant tensor. And that's exactly the cubic form. Okay? And so basically, and so the cubic form vanishing is that these two tensors are equal. And so in that case, of course, if you have the geodesics being straight lines, and this actually gives you the Klein model of hyperbolic space, which corresponds to the hyperboloid. Okay? All right. So the next thing I'd like to talk about is a little bit more about. So I want to say that this is kind of a local to global. And so if H is an immersed hyperbolic affine sphere, with the complete affine metric, then it's of the form mentioned above. So this is kind of basically due to Cheng-Yau, and kind of with some kind of clarification by An-Min Lee. So of the form above means that, well, it is properly embedded, and it's also asymptotic to the boundary of a cone. And the way I've kind of defined things, I'm kind of normalizing it so that this, what you call the center, is always going to be 0, and there's some other normalization. But that's the basic theorem. Okay? Okay. And so this is actually a way of producing these objects. So if you can somehow have, through some differential geometry, if you have kind of the structure of a hyperbolic affine sphere, and if you can show that the affine metric is complete, then you automatically get this cone picture, which is quite nice. Okay. So the next thing I'd like to talk about is a little bit about kind of switch gears a little bit and talk about families of convex domains. Okay. Okay. So what I would like to consider is kind of omega, again, properly convex. As a subset of RPn in the same sense. And you can consider this with, you can consider the space of all such domains with the Hausdorff topology. So you just use kind of a standard metric on RPn, Fubini studio metric. It's something like this. And then we're interested in projective invariants, so we want to mod out by the action of the projective linear group. Okay? So it turns out that this this kind of problem, as I've stated it, is not naturally. So this, it turns out that this quotient space is not so nice, and in particular, it's not Hausdorff. Okay? And so I can give you an example of this. So, and so I found kind of this example. I mean, Bill Goldman has some lecture notes that are on his website at the University of Maryland. But the example is probably quite standard. So let's say we have, we'll just do this kind of a two-dimensional domain in RP2, like this. But I want to assume that it has a corner. Okay? So if you have a corner, then what I'm going to do, so what I mean by a corner is that, well, it does have kind of tangent lines here. Oops, let me draw it a little bit better. So it does have tangent lines here. And what I can do is I can make these, I can complete this to make a triangle here. Okay? And I'm going to put coordinates on this so that, so in coordinates, I'm going to label the vertices of the triangle. Say this is 0, 1, 0, 1, 0, 0, and 0, 0, 1. Okay? This is kind of the standard coordinates on RP2. And then what I'm going to do is I'm going to let the following diagonal matrix act on omega. And as t goes to infinity, and you notice that since this is diagonal, then the eigenvalues of this this matrix are exactly, or the eigenvectors when you project down into RP2 are exactly projected at these points on the triangle. So they're fixed under the projective action. But as t goes to infinity, well, these two coordinates get bigger and this one gets smaller. So in this case, if this is omega and this is, say, rho t, then rho t of omega goes to this triangle. Okay? So this example immediately shows that this space cannot be Hausdorff because the triangle is in the limit of omega under this action of PGL n+1. Okay, and there are similar examples you can also write down if there's if you have omega which has a boundary point which is strictly convex in C2. There's a similar example where you can write down so that the limit of omega is the interior of a quadric. Okay, so so this is not, and so these limits are going to be important later. But it turns out there's a better way of looking at these, a better space we can consider. So so we could kind of let F be equal to this space where, so omega is as above, and x is a point in omega. Then there's a kind of a theorem of Benzacry that says that F divided by this PGL and R action is actually compact. And so I mean compact in the French way, so that Hausdorff is compact and Hausdorff. So, so in particular, you can take these sorts of limits. Okay? And then there's, so it turns out that there's a way of kind of using this. You can kind of use this Benzacry compactness to get many estimates on projective invariants. Okay. And so the first thing I'd like to mention is that there's a theorem of Benoit and Hulin, and so this was published in 2013, that you can use this to show that, so basically the affine metric and the Hilbert metric are by Lipschitz. And this is kind of by Lipschitz in a strong sense. Let me say kind of uniformly by Lipschitz, where kind of the Lipschitz constant only depends on the dimension. And so what you can do is kind of the idea of the proof is to kind of consider a point in the tangent bundle over omega. So x is an omega, and then v is a tangent vector. And then you can kind of consider the norms here of v, the Hilbert with respect to the Hilbert metric, and with respect to the affine metric. So there's kind of this universal constant, and basically what you do is, well, you can kind of use this Benzacry compactness and kind of a little bit more to analyze the quotient. And so the quotient of these kind of limits, as x goes, say, to the boundary of omega, well, you can still use Benzacry compactness to kind of find a new space which has kind of the same basic properties, and you get kind of the same sort of limit. And so this is a positive, so if you look at kind of the quotient of these things, it's a positive continuous quantity on a compact space. And so it's bounded above and below. Okay? Yeah. It uses the fact that they're projectively invariant and also they're continuous with respect to the Hausdorff topology. So I think this is quite straightforward for the Hilbert metric. You need to mess around a tiny bit with the Monge-Ampere equation to do this for the affine metric, but it's still true. Yep. Which domain is the worst? Oh, you mean when is this constant the worst? I'm not sure. I mean, I assume, I don't know. Is it the I would assume the simplex is the worst because it's always the worst, right? But I haven't worked it out, so yeah. Okay. All right. So this is kind of a very nice technique, and kind of Benoit and Hulin kind of used this Benzacry compactness to introduce a lot of estimates to the study of these projective invariants in this affine metric. Good? Okay. So the next thing I'd like to talk about, so let's see if I can do this. Okay. So the next thing I'd like to talk about is there's kind of some special cases in dimension, special properties in dimension 2, which make this kind of very easy to analyze, or possible to analyze a lot of things. Okay. So the case of dimension 2, and so the affine metric, in particular in dimension 2, this will give you a conformal structure. Okay? And so this is, I mean, it may or may not be so very interesting if you're just talking about a domain, but I'm also going to be considering quotients. So there's going to be an analog of Teichmüller type theory coming up. And moreover, kind of the cubic differential, is maybe I should say the cubic form is the real part of a holomorphic cubic differential. Okay? So what you might call kind of so in this theory, there are going to be cubic differentials as opposed to quadratic differentials, which are more common in Teichmüller theory. And so this is not particularly, should not be particularly surprising, because as I've defined it, this comes from an elliptic equation, right? In dimension 2, there's an invariant metric, you get a conformal factor, and then you expect kind of the natural invariants that flow out of this, such as the cubic form, to be related to holomorphic or at least harmonic objects. So this is not too surprising. And so these are related by, so there's an elliptic PDE for the conformal factor. And so this is first written down by C.P. Wang, but kind of in a slightly different situation. This was written down over 100 years ago by Tsitseka. So if you satisfy this differential equation, so what I want to do is I want to consider not just, I want to consider a conformal background metric. K, and then I want to figure out what sort of conformal factor I need to multiply K by in order to get the metric for an affine sphere. Okay. And so if you satisfy this elliptic equation, so Laplace V, this is with respect to K, plus 4e to the minus 2v, the norm u squared with respect to K, minus 2e to the v minus 2 kappa. So this is the Gauss curvature with respect to K is equal to 0. Okay. So in this case, then e to the v times k is the affine metric. Okay. And moreover, U is the cubic differential. Capital U is the cubic differential. Small k is the background metric. So I have a conformal structure, and I don't just want to consider norm dz squared as the background metric because I really want to work on Riemann surfaces soon. For instance, the hyperbolic metric. So if this is, and if you know a little bit about kind of these sorts of equations, this is very, very similar if you just replace a few things, you say this is a quadratic differential, and you erase this 2, and maybe you have to mess with the constants a little bit, but not with the signs, then this is the same equation that I guess Mike Wolf studied in looking at harmonic maps between hyperbolic surfaces, and his kind of way of approaching the Thurston boundary with that respect. So this is, but in any case, this is a very nice equation. And let's see, what was I going to say? So, and moreover, given, say, a Riemann surface, with a background metric K, a holomorphic cubic differential V, capital U, and this conformal factor satisfying star, we can locally integrate the structure equations for a hyperbolic affine sphere in R3. And so I guess in this situation, this is again, strictly noticed by C.P. Wang, but this is really, Tsitseka was kind of is usually described as the first person to study affine differential geometry about in 1908. But he really had kind of this sort of integrable systems property in kind of a very slightly different situation where kind of a few signs, he was considering saddle-shaped surfaces that were not convex. But he really had the relationship between this sort of equation and being able to integrate structure equations locally. Okay, so we can locally do this, and this is exactly the sort of situation that we would like in order to kind of apply this local to global property. Okay, so that almost went up far enough. Okay, so I guess, so given this sigma in the background metric, U and V satisfying star, then if this, once you multiply by the conformal factor, this e to the vk is complete, you get kind of the universal cover of sigma is embedded into R3 is a complete hyperbolic affine sphere. Okay. So in particular, you can consider so in particular, you get this by Cheng-Yau's theorem. You get this structure just purely from kind of these local considerations on a Riemann surface, together with solving this differential equation for V. Then you do get this global structure of H, and so you have, I guess, sigma tilde, which is going to be the unit disk. Then you do get this sort of picture. Okay. And so in particular, what you can do is this so in particular, in kind of in the case where sigma is compact and the background metric is hyperbolic, so kappa is -1, then there exists a unique solution to star for each cubic differential. Okay? And so in particular, you can use this to look at pairs of Riemann surfaces, if it's compact and has a hyperbolic metric, so genus at least 2, and cubic differentials. And these are equivalent to, and so I haven't defined this yet, but I'll call this a real projective, or say a convex real projective structure on the surface. Okay? And so this is, I guess, C.P. Wang did some work on this, and Labrie did some work independently, and I noticed this as well independently. So, I use C.P. Wang's result. And so this is a way of describing kind of the Teichmüller space of all these convex real projective structures. So basically what this is quotients of convex domains by projective linear actions. And you can describe it in terms of this holomorphic data. Okay? So these convex real projective structures, this is going to be given by writing this convex domain omega, where this gamma is kind of a discrete group in PGL3R that acts it acts such that the quotient is a surface. Okay. So these sorts of structures can be determined by this sort of holomorphic data. All right, about 10 minutes. Okay, so one of the things that I've been working on for a while, and then is, so there's kind of this gives kind of a nice description of this, and I guess maybe I'll just kind of, so I guess I'll say that I'll call this a theorem, and then there's a corollary, which is the theorem of Goldman, is that these this deformation space of convex RP2 structures is homeomorphic to a ball of dimension 16G minus 16. And so basically what you can do is, you know, the Teichmüller space has real dimension 6G minus 6. It's homeomorphic to a ball, as Anna mentioned. And then you also know the space of cubic differentials over a given Riemann surface. You can use Riemann-Roch to figure out that dimension. And so that's complex dimension 5G minus 5. You add it up, you get real dimension 16G minus 16. So this is kind of really an analog of Teichmüller space. And this affine differential geometry is a way to use some differential geometry to kind of relate this to holomorphic data. Okay. All right. Okay. So one of the things that so once you have kind of this description in terms of holomorphic data of this deformation space, you can ask yourself, well, one of kind of a big area of research is, well, what sorts of the properties of Teichmüller space, which has an extraordinarily rich structure, which ones can we possibly extend to kind of find some nice geometry of the space? And the one that, so maybe I'll just kind of say, kind of this is an idea, is to try to use this description to extend the geometry of Teichmüller space. And this is actually an extension because, so you remember kind of the cubic differential is what is U. So this, if U is identically 0, then you can use this theorem of Berfeld to say that, well, that's exactly the case where this hyperbolic affine sphere is going to be just a hyperboloid. And that's exactly the case of, I mean, you might call these, I guess, the Fuchsian real projective structures in this case, the ones that just come from the Klein model of the hyperbolic metric. Okay, and so Teichmüller space does sit naturally inside of this space as the zero locus. And let's see. So to try to extend this to the geometry, and so one of the things that, just to kind of mention a little bit, non-compact cases. So I guess one of the things that I did a while ago, I think it was published in 2004, but I need to kind of look this up, is that what I want to consider is a punctured Riemann surface. And the cubic differential U is going to be, maybe I should not say punctured. Let me say nodal. So the punctures are kind of matched up to each other, as in the boundary of the Deligne-Mumford boundary of the moduli space of curves, with what are called regular cubic differentials. And so this is going to be kind of U is allowed poles of order less than or equal to 3 at the punctures. And I guess there are some residues match up at the two sheets of the node. So this is kind of the way algebraic geometers write this. So we would say that each of these sheets has a puncture, and I'm allowing kind of poles of order 3 at this puncture, and the residues have to, which is kind of the z to the minus 3 coefficient, they have to add up to 0 in this case to be regular. Okay. And so this regular cubic differentials, this is naturally the extension of the holomorphic vector bundle over, I guess, the Teichmüller space, but also descends to the moduli space, just kind of considering cubic differentials there. If you go to these nodal curves, then the space of regular cubic differentials is the kind of a natural completion of that space. Okay? So these are kind of natural limits. And so I've kind of studied this, and it turns out that kind of in this case, the residue determines the geometry of the ends of this of the RP2 surface that you construct in this way. Okay. Another case, which you can think of as so another case is kind of on a disk. It's kind of the standard Poincare disk, and in this case, you might assume that the cubic differential is bounded with respect to the Poincare metric. So the cubic differential, you just take its sup norm, you assume it's bounded. Then recently, Benoit Noulin and a preprint. So I think this is to appear in JDG. They can kind of kind of solve this equation, and actually they have kind of a nice description. This is going to be kind of an analog of a universal Teichmüller space. Okay? All right. And then in Benoit Noulin's 2013 paper, I mean the same one that I mentioned before, they considered the case of, I mean it's essentially, they didn't phrase it this way, but it's essentially kind of a partial converse to this statement. So basically what they're doing is, what I've done in this 2004 paper is given these cubic differentials, I want to construct the real projective structure, but I didn't have kind of a way to go back yet. And so they used these estimates in the Binzik recompactness to go back in the case of, so they're going to consider the case of finite volume or finite area, either with respect to the affine area or with respect to, there's a natural Hilbert area. So those are also the notion is the same by this Spencer-Cree compactness result. And so what they considered is, in this case, then U is, so in particular, this Riemann surface has, at worst, punctures. So there's no kind of disks at infinity that you would have to fill in. So conformally, it's just punctures. And U has kind of poles of order at least 2. So they didn't quite address this kind of pole of order 3, which is in some sense kind of a generic degeneration. But in this case, of the poles of order 2. And I guess I should, I don't really have any time, but I should mention, kind of in this case of finite area, I mean, earlier, Marquis had shown that kind of in this case of finite area, you can actually figure out what the real projective structure of kind of the RP2 structure in this case is one of kind of what you might call a parabolic holonomy. So in particular, so I'll just kind of describe this in terms of a fundamental domain. You have omega, and then in this case we have kind of a discrete group action. So in this case, with the parabolic holonomy, there's kind of a single fixed point, and then you can consider kind of fundamental domains that are, in some sense, that are going to be ideal polygons. And so near this fixed point, you have fundamental domains like this, and so the holonomy looks like this. And so if you look at the Klein model with respect to kind of a hyperbolic cusp, then this is exactly kind of the picture you get here. And so Marquis, so this is kind of essentially relating this sort of an end to U of pole of order less than or equal to 2, which I would call kind of a 0 residue. And kind of recently, in kind of some work in progress, I've done the same thing with kind of poles of up to order 3, and I'm currently working on, I'm not willing to claim publicly anything about families. But I think all this sort of stuff, this kind of use of this Spencer-Cree compactness and the estimates that you get from that are quite powerful in this situation. So, thank you.
If you take this solution by Cheng-Yau, they construct some function which is 0 on the boundary and convex, so it will have some minimum inside the domain. Is it known at which point this minimum is attained?
No. But the function itself is not projectively invariant, so.
Oh, okay, so the point, so the minimum will also not be projected.
No, because I mean, if you consider this, I mean, you kind of throw this up to this cone, and then you consider linear actions on the cone, and of course they may not preserve this n+1 coordinate where omega lives.
Thank you.
Any other questions?
If you take a convex cone and you cut with hyperplanes in such a way that the bounded portion of the cut has constant area, do you get something that also a convex hypersurface that is asymptotic, and can you do something with it?
I'm not sure. So you take a convex cone,
and then you cut with hyperplanes, let's say, and that such that the bounded part of the cone always has volume 1.
The bounded part of the cone has volume. Oh, so you're cutting off a, okay.
Yeah.
And what was the?
Well, that's what happens for the Lorentz cone. So do you still get a convex hypersurface? Because that would be a invariant under special linear group. And
Yeah, there are other cones. I mean, there are other hypersurfaces. There's kind of a Vinberg has kind of a natural invariant function that he and then he takes the Hessian of that to have an invariant metric on the cone, but you can restrict that. The level sets of this are hypersurfaces that are similar to this, and they restrict to and kind of the metric restricts nicely. So I don't know how this relates to what you're talking about, but I know kind of the Wennberg, at least for this kind of Wennberg hypersurface, I don't believe it is, you have this duality property under the conormal map. So that, I mean, this is related to, so you know, it's like one of the classical properties of Legendre transform is it takes solutions of, not the Monge-Ampere equation I wrote down, but kind of determine the Uij equals to ij equals to 1 into kind of solutions, dual solutions. And so I think that in terms of a conormal map, having this PDE to back you up is more natural. I mean, it's harder to write things down because, I mean, basically there are, I wrote down the 2 examples that you can do. I think you can do other examples now in terms of special functions, but it's not. I think Calabi did this, and I think Dumas and Wolf have looked at it recently, but it's not clear how much of that sort of thing you want to do. So.
Any other questions? Yeah.
Can you try to explain or re-explain in simple terms the idea of the affine normal and what is a affine sphere in general?
Yeah,
in this Blaschke theory.
Yeah, I didn't explain. So I gave the definition of an affine sphere by just writing down the differential equation, because that was shorter.
Yeah,
but,
I realized.
Yeah, but if you want me to explain, so I did. So maybe I could say another definition, kind of a hyperbolic affine sphere. And so this is going to be normalized. So basically, I normalized by shifting the center to 0, and there's some sort of scaling as well. This can be defined by is a convex hypersurface. And so you can define this for non-convex hypersurfaces as well. There's kind of a version of affine sphere, but I'm not interested in those. Whose position vector f is always equal to c, the affine normal. Okay? And so that's what I didn't define as the affine normal. So the affine normal is, so given any, so let's call this H, or hypersurface, so given any transverse vector field, C tilde to H, then you can kind of play this game instead of X and Y are tangent vector fields. Then what I want to do is I want to consider this standard structure equation. I want to take this, this is the standard flat connection on Rn plus 1, dx y. So this is still going to be a torsion-free connection. This is still going to be a symmetric tensor, and if C is pointed in the right way, it's going to be positive definite, since H is convex. But there are also some other equations which I didn't write down, which I didn't need to in the case where I was just dealing with F. And that is I want to be able to differentiate C with respect to X. And so in that case, you have, again, so these are going to be the tangent parts. And this is going to be the part in the span of C part. So this is naturally an endomorphism on the tangent model. This is a tensor. This is a one form. And the condition, and I guess I'm putting tildes on these. So this may not be. So C tilde is the affine normal if we have two conditions. So I guess one is, so this is in some sense a choice, but I want C tilde to be pointing to the convex side of H. So this picture. 2, this tau part vanishes, and there's a name for tau, but I don't remember what it is. I mean, Nomizu and Sasaki have a book on affine differential geometry, and there's a name for that, but I don't remember what it is. And the third condition is that this metric, this affine metric given by the second fundamental form, its volume form has to agree with the volume form on Rn plus 1. And that's where you get kind of a Monge-Ampere equation, because the second fundamental form is naturally kind of a second derivative of something. But it's, so let me just kind of write this down very quickly. So determinant in Rn plus 1, so these are going to be, so x1 to xn, or tangent vector fields. So if you join C to this, then you can take a determinant. You square this. And then you take kind of the determinant of the second fundamental form. If these are equal, so that's what it means for the volume form, which is the square root of this, to agree with the volume form on Rn plus 1, where you kind of do something similar to an interior product with the affine normal. So that's one way of defining it. You can also, Blaschke has a more geometric way, but that's what you wanted. Yeah, okay, sorry. Well, the more geometric. Yeah, yeah. No, this is, they're all the same. But this you can actually compute with. And so maybe the more geometric way is you kind of, I don't know if I have time or not. Okay, it is very quick. Yeah, you take the tangent plane, you move in. Okay, so sorry I did the wrong one. But, so the more geometric way, so you have kind of x, you want to consider C at x. And so what you want to do is you take kind of the tangent plane. So this is, say, the tangent plane. Txh. And then you move this in. So you consider kind of into h. So you consider kind of parallel planes to this. And these parallel planes, they will cut off solid bodies of this shape. And then you consider the center of mass of the solid bodies. And that is a curve which goes to x. And then its tangent vector is the affine normal. And this is not quite well defined because I need to, this gives you the direction, but you can normalize the volume. You're now allowed to use the volume in this situation to kind of scale how far in you move these tangent planes. So.
You also have a direction to define spheres by the condition that all these affine normals are congruent, or it's
I think that is strong enough. So yeah, just like if you try to do this trick with Euclidean geometry, if all the normal vectors point to the same point, then it's a sphere. So in this case, yeah, it is strong enough. And so this is kind of a hyperbolic affine sphere where kind of the center would be out here. There are elliptic ones where the center is in the middle. There are parabolic ones where the center is at infinity. So.
Any other questions? Say I had one.
Okay.
Can you say anything about the sectional curvature of the simplex solution?
It's flat.
It's a flat metric?
Flat.
I see. So, okay.
But you can see, I mean, you can write down an Rn action. You can put that in SLn plus 1 easily. It's like R plus to the n.
Yeah, okay, yeah. Okay, thank you. And yeah, let's thank the speaker again.
Thanks.